Hello, everyone. I'm Sean Buckley, Editor-in-Chief of Lightwave, and it's my pleasure to welcome you to today's Lightwave webcast, where we'll discuss the 800G migration reality, scaling DWDM networks without redesign. This webinar will explore the real-world considerations of migrating to 800 gig and DWDM and OTN environments. Attendees will learn how 800 gig impacts fiber capacity, how to navigate upgrades within existing brownfield networks, and what practical migration strategies are available, including FlexGrid architectures, L-band expansion, and phase deployment models. To discuss these factors and how to strategize around them, it'd be my pleasure to moderate a presentation by two industry experts. First up is a veteran of the industry, and that's Lawrence Gassman, President of Communications Industry Researchers, followed by Erik Garland, Director of Sales for PacketLight Networks, who is also the sponsor of today's webinar. But before I hand off things to our speakers, let me quickly review our webcast setup for those of you who have maybe joining us for the first time or for the first time in a long time. I'll start with the Ask a Question box you see near the slide area. I invite you to feel free to use this to ask questions at any time during the event today. To submit a question, just click on that box, type your question, and hit the send button. We'll address your questions after everyone has finished their presentations. Now, in the event that you run into a technical problem during the presentation, you can call for help via the Q&A tool. Just describe your problem, hit the question submission button, and Milan, who's today's webcast technician, will be happy to help you out. Next, you know someone might benefit from seeing this webcast. You just want to revisit the presentation yourself. The event will be available on demand from our webcast archive for the next several months. We'll send you an email with a link to the archive sometime in the next day or so that you should feel free to forward to your coworkers. And the archive version of the webcast will be accessible from the webcast archive section of our website, which you can reach via our homepage at www.lightwaveonline.com. Also, if you'd like, you'd be able to download a copy of today's slides via the Event Resources tab. You should see in your screens right below the Ask a Question box. Just click the tab and reveal the slide files. Also, before I go, I just want to mention to those in our audience who hold a professional credential from Bixby, I'm pleased to let you know that this webinar qualifies for one continuing education credit toward your credential renewal. I'll provide more details about the CEC and issuing an attendance certificate after our presentation concludes and before we begin Q&A. But with that, I'm going to just advance the slides for Lawrence. And Lawrence, the floor is yours.
Thank you. So I can't actually see what you can see. I ended up doing this from my phone. So I'm going to shift for me, but I think we're still on the first page, which is basically just my information if anybody wants to get in touch with me. We do all the usual things, publish reports, both actually in data center markets and in quantum markets. Long story, we wouldn't have time for that. So I've been around for a while. I started doing this kind of work in the 80s. And in a way, you know, what's new? We're upgrading the network. Except it is now multi-dimensional, because it used to be that upgrading the network just meant you were moving from a megabit to a gigabit to eventually a terabit. And now, of course, we've got, many problems, of which probably the second most important is latency, and that comes from data centers, which back in the day used to mean something like a wiring closet, but now means something the size of Manhattan, and very expensive. If you go to the second slide, that's actually an out-of-date estimate that I put together on the expenditures on AI data centers, and it's a lot of money. And as you upgrade the network, you're spending a lot of money, partly to get a network that works, but also, and that's really what we're talking about in the seminar, is to get a new set of tactics and strategies that make the old one work in new ways. The point being that, as always, you can't completely rebuild the network every time there's a new application. Okay. The 800G changes everything. the quote Cindy Lauper about money, and it's going to get worse because, of course, we're going to move to 1.6 terabits before too long, and then on to 3.2. Don't think there's too many 3.2 terabit systems out there. And that, as I said, the original problem with all this kind of upgrading was speeds, but there's not so much problem in getting to 800G per se, but given the DWDM and related architectures that have emerged in the last, 20 years or something, the skill is not just getting to 800G, but doing it without completely screwing up the DWDM architectures, and that's what I'm going to talk about today, and there's a large number of ways of doing it, and the way that you actually do it will depend very much on what kind of network you have, what's already in it, but there's a few things that you can list, and I guess go to slide 3 now. I guess I've got another way of putting what I just said is most carriers, cloud providers, let's say none of them can justify forklift upgrades across long-haul, metro, and DCI infrastructures. They might be able to do part of it, but seldom all of it. So, the cheap, the first thing you look at is, do you really need 800G? Where do the economics truly work? And I'm going to suggest that this needs to be the number one priority. It doesn't exactly get you where you want to be if you really have to re-architect the network, but it shows whether you're going to need this now or soon or at some point in the future. And I suggest it's because of an experience I had very recently. I suggested it's done by a real economist who knows how to look at costs and put it all together in a reasonable model. So that's the first thing, I think. Know whether you really need this. You probably do. The second one is reusing existing line systems, because that's not cheap either, but it's obvious and you can keep the costs under control. But I'm thinking, and we're going to publish a report on pluggables. Nobody talks about pluggables anymore, but you need to, on coherent pluggables. That should be coming out in a few months, because that's really where you end up going with most of these upgrades. And of course, while we like to talk about co-packaged optics and external lasers and all this really cool stuff, there's plenty of pluggables around, and they're going to go on being that. And that's once you've decided you need to make an upgrade, ZR and ZR pluses are probably where you look first. And then, so just to to go back, you look at some of the numbers around your particular network, and then you start thinking about pluggables and upgrades of line systems. And then you start going to the more exotic things like IP over DWDM. And then the really exotics, which I find very interesting, is you can't, it's always been assumed that data centers will be run by human people. The problems that come up are not so great that you can't all get together. Excuse me, sending up some notes. You can't all get together and fix them. But when you get to 800G and presumably when you get to 1.6 and when you get to 3.2, humans aren't good enough. It's sad. But everything's happening at once. And you've got to look at non-humans, which interestingly enough means AI, which means, of course, that you're using AI to run AI data centers, which is fascinating in itself. And the the things you're trying to look at, and again, you've got to look at these all at once, is that I'm not sure which are the most important, and probably depends on network to network, but you've got things in your network that need to be changed, and you need to optimize the change so that you end up having what you want. And they're usually ROADMs from different vendors put in at different times, and you can probably say something very similar about amplifiers. Then you've got fiber. Officially, we all know where the fiber is, except that we don't. That comes from different vendors, and even more important, some of it's been in there for a long time. And there used to be this old story from AT&T that sharks eat fiber, which apparently they do. But some fiber's in decent quality. That this may be the time to do something about. And then you have the 50-year-old problem of multiple optical vendors, although standards do help, obviously, a lot with that. So all these things have to be handled at once, and humans aren't necessarily the way to do it. So you're going to get AI impacting AI, and there's a science fiction story in there somewhere. These aren't clean upgrades, and that's another difference between the old kind of upgrade when you're talking about moving from 100 gigabits to perhaps 200 gigabits. It's just much more challenging, and that's the one takeaway you should have. So you've got to decide where you're going to put something. And one other thing I didn't mention is, okay, so you're going to put in the CR pluses pretty quickly in your upgrade, but and you're going to put in automating spectrum and performance management, because otherwise you're going to have even more problems. But you've got to look at the line systems as well, which are DWDM, which is in the title of the talk. And some of them will be able to be reused. So it's a mess. And I think if you go into it not understanding it's going to be a mess, which means leaving sufficient time to upgrade things, then you'll be disappointed with the end results. Sorry, I'm flipping over a couple of pages.
Lawrence, thanks for that. I guess we just need to keep moving on. but yeah, you presented some great topics here. I look forward to exploring more of it in the Q&A. But thanks for your great insights here. Thank you.
Sure.
Okay, great. And okay, we're going to move on to. We'll hand this off to PacketLight. Here you go. Yeah. I think you're on mute.
Correct. Yeah, thank you, Sean. Can you hear me now?
I can hear
yes,
you.
I can hear you. You're good. You're good. Thank you. Yep.
Yeah. Well, thanks, Sean. Thank you, Lawrence. Welcome, everyone. I know there's friends and colleagues out there in the audience. For those of you that I haven't had the opportunity to meet, maybe sometime in the future. But thank you all for joining from a global audience perspective. What I'm here to talk about today is about, the nuts and bolts behind 800 gig networks, but not in the simplistic sense of when we're talking about 800 gig and that's the next speed. And we're not saying that everyone should move to it. I think the real challenge is that when we're introducing 800 gig, it changes the design conversation, and it changes how we think about spectrum. It changes how we think about fiber utilization. It changes how we approach brownfield upgrades. It impacts our equipment choices, our architecture, our timing, and even our procurement risk. So what we're here to talk about today is really the 800 gig migration reality. And at a high level, what we'll cover today is, what are some of the drivers behind 800 gig networks, what it is and what it is not, and why it's often harder than anticipated. Then we'll cover some of the areas that we see as practical strategies for scaling your capacity, and like Lawrence mentioned, without creating a redesign problem down the road. So with that being said, we'll kind of jump into today's agenda. The conversation topics that we'll cover in line here are, we'll first take a snapshot at the industry trends over time and some of the shifts that are driving 800 gig requirements for today. We'll talk about critical insights into 800 gig networks. We'll cover the migration challenges that we see coming up and available ways to navigate these transitions. We'll discuss the IP over DWDM versus optical layer, type of conversation. And importantly, we're going to cover the economic drivers behind 800 gig adoption. And to round things out, we'll talk about solutions, strategies, and importantly, phased approaches that can set you up for immediate success, but also for long-term scalability as we navigate from 800 gig to the 1.6 and 3.2 terabit networks of tomorrow. So I think we would be amiss without addressing the first major change that's really driving the conversation topics around 800 gig, and that is that the traffic pattern itself is shifting. So for many years, network growth was significant, but it was relatively understandable, and operators could forecast service growth, they could add wavelengths, and they could plan capacity expansions and do all of this on a multi-year horizon. And in today's environment, that's no longer the case. The AI workloads and compute workloads that we see today have shifted and introduced much more aggressive growth models for network capacity. And these are highlighted, especially when you're looking at data center interconnects environments. You're talking about training clusters, you're talking about inference clusters, storage synchronization, east-west application traffics, and the distributed compute architectures that are creating large flows between sites. And essentially that means two things, right? So first, it means that your traffic growth is not just increasing, it means that the traffic growth itself has become less concentrated, it's become more bursty, and it's also become less forgiving. So what we really need to highlight is that the demand for network capacity has become less predictable. And secondly, is 400 gig adoption has just recently stabilized for a lot of operators and is already becoming insufficient in some environments. So at the same time, the planning cycles are shrinking, and what we used to design on 3 to 5 year horizons is now being looked at on a 1 to 2 year horizon, and in some cases even shorter than that. And that is exactly why this is not a normal capacity upgrade cycle. AI has been breaking the planning assumptions that underpinned the earlier optical network evolutions that were put in place. And so the way that we see this is the question is no longer, how much the traffic will grow. It's more of a question of if your network can absorb that growth without repeating redesign down the road. So essentially, now that the traffic pattern has changed, the technology stack is changing behind it as well. So let's take a quick look at the history of network capacity demand, and I think this is going to help shape the perspective for the rest of today's conversation. So historically, capacity growth has been linear, and that's no longer the truth. It's become step-based and unpredictable. So high performance compute, AI, machine learning workloads, all of these are introducing sudden large demands for capacity rather than your traditional gradual growth. In the traditional model, the more linear blue line that you see at the bottom here had linear growth and even spacing. It means that it was steady, it was consistent. Expansion over time could be planned at regular cadences with predictable intervals for your growth strategy. in today's model, in what we call more of an AI-driven model, it's extremely uneven, it's unpredictable, and requires bursts in capacity requirements. So this means you're going to get sharp spikes with steep step function jumps, as the green line dictates, meaning that the capacity needs are going to arrive in irregular waves. But when you take a look back in time over the evolution of optical capacity growth stages, when we started with sub 10 gig systems, moving through 100 gig, 200, 400 gig, and now into 800 gig and beyond, I think it's important to note here, as we follow the industry trends, is the pressures and demands for network capacity have historically and continued to be driven by technology innovation. So if we look back to the early network days, circa 95 and 2000, with the dot-com era, and then we advanced in the early 2010s into the era of OTT streaming, social media, YouTube, Netflix, etc. And then in the mid 2010s, we introduced public cloud. And then now in the 2020s, we're introducing AI, machine learning, and there's technology innovations with quantum computing and stuff that are coming down the horizon. And so it's really good just to know that these demands are not coming just from a sheer volume perspective. It's that they're driven by technology innovation. So back in the 200 and 400 gig era, this is where the DWDM platforms that are in place today and the OTN systems evolved beyond just simple transport methodologies. That's really when the operators began standardizing on OTN switching and grooming, and allowed the networks to aggregate services more efficiently, but also to optimize how capacity is being used across the network. Now, as we kind of transition our mindset into 800 gig, we're seeing a really important shift, and Lawrence touched on this earlier, is that we have coherent pluggables becoming mainstream, your ZR, your ZR Plus classes in the market. And these improvements in the pluggable technologies are influencing how the operators think about where the optics reside on the network, and also how capacity is deployed. So at the same time, we've got increased pressure for more modular and flexible transport architectures. But the client sides, the customers are expecting the DWDM and the OTN platforms to support incremental scaling, not across one line rate, but across multiple service rates. And they're asking for this with simpler deployment models. And the operators are expecting all of this without requiring full systems and network replacements. So a tall ask, right? But doable. And I think the key takeaway here is this isn't a conversation about higher speeds. It's about designing DWDM and OTN platforms that can evolve with optics and capacity demand, all the while providing and maintaining stability for the rest of the network. And a key development here is kind of a mindset shift, right? That architecture has been commercially relevant. And what I mean by that is, historically, a lot of organizations separated their technical architecture and their procurement strategy. But in today's market, those two are directly linked. So, I do want to make an important note here that, when we talk about 800 gig networks and network upgrades, not all network segments feel the pressures in the same way. So let's take a quick look at some of those network pressures. And when we say that 800 gig is becoming important, every network has a different business case. So let's look at a couple different classifications here. For example, the data center interconnect environments are driven primarily by AI clusters, cloud interconnects, large east-west data flows, but their constraints are density, power consumption, and footprint. And these are in environments, dense data center environments, where every rack unit and every single watt matter. Now, when you kind of go out a little bit further into the metro networks, you're seeing the growth drivers is driven more by enterprise aggregation on the front haul evolution. It's driven by service flexibility, and the constraints in that market tend to be space and fast turnup, but they also need operational simplicity to scale. Now, when you get even deeper and you look at long haul, the conversation shifts yet again. So the drivers in long haul are primarily backbone growth. They're major route upgrades, and in some cases, really long terrestrial transports or even subsea transports. And the constraints there are primarily dominated by physics, on optical physics. So your reach, your optical signal to noise ratios, your signal degradation. So even though 800 gig has become relevant across various segments, the reason to deploy it and the design trade-offs that we see are not exactly the same. So with that being said, let's take a look at the bigger technology shift that's underpinning all of this. So right now we see, in today's market, we see three strategic shifts that are happening in the optical networking world. And that first strategic shift is a migration from fixed grid into flex grid technologies. So historically, networks used fixed spacing approaches, for example, 50 GHz, 75 GHz, or 100 GHz channel spacing. And that worked well when the service rates and the channel bandwidth requirements were much more predictable. But when you start to mix these service rates, right, and you're talking about 100 gig, 400 gig, 800 gig, and the next evolution of 1.6T and 3.2T classes of transport, these fixed allocations become extremely inefficient. And that's because some of the signals consume in this model too much of the reserve spectrum relative to what they actually need, while your other classes cannot fit into these fixed models. The second strategic shift that we see is from single rate spectrum planning into a mixed rate spectrum planning. So instead of assuming that the whole fiber plant is built, primarily around one dominant line rate, the operators of the world today are increasingly needing to carry multiple rates, but they need to do it efficiently and at the same time. And the third strategic shift is from optimizing capacity per wavelength to optimizing total capacity per fiber or fiber pair, right? And that's a subtle but really important change, because the question has evolved from what is my line rate to how do I maximize and get the most useful, scalable, and commercially attractive capacity from my own fiber assets over time. So those are the three strategic shifts that we see happening in the optical networks. And we also have to address something that's just as important and frankly often overlooked. So even if we have the technology exists, it does today. And if the architecture supports it, right, the plan supports it, there's the ever-growing question of whether you can actually deploy it when you need it. So let's address the elephant in the room, and we'll kind of cover briefly a critical constraint that we see in the market today. And that is your component shortages and lead times. And this is centered primarily around DWDM and OTN equipment. The lead times have been stretched significantly, and we're seeing reports of timelines in 9 to 12 months. And depending on your specific platforms, your OEMs, your componentry, all of those components play a factor into the lead times. But these constraints are really centered around the conversation topic today, around your high bandwidth optical building blocks. So when you're talking about coherent DSPs, you're talking about the high-speed pluggable optics and the advanced components that are used in network operator systems like your ROADMs and your amplification systems. So, and to layer onto this, we're also seeing large buyers and hyperscalers that are, out there consuming and locking in supply through major long-term agreements, and they're consuming a very large portion of today's available manufacturing capacity. So, now the conversation has evolved even more, and we're talking about capacity growth that is not just a technical design question, but it's also become a supply and timing question. And, I think what this means operationally is it means that the fiber may be ready, the sites and the planning can be ready, the business and the commercial cases are ready, but the equipment may not arrive when it's needed. And the impact here is often understated because this impacts a lot of functional areas. It impacts your data center and your interconnection expansion strategies. It impacts your service activation. And in most cases, that's tied directly to your revenue recognition and your customer onboarding. But something that sometimes gets lost in this as well is as time goes on, it can also force your existing network to run hotter and closer to their limits for longer periods of time. And that puts people in an uncomfortable position. So these are exactly the reasons why we're having the conversation around why architecture matters today more than ever. Now, when we're operating in a constrained supply chain environment, the competitive advantage is going to go to the network that can scale incrementally and efficiently and keep pace. And so we're seeing this really driving supplier diversification efforts across the board, because providers are needing to ensure that their sourcing strategies allow their organization to acquire the necessary solutions and the technical capabilities on timelines that meet their needs. So most of the time, this diversification effort has led to desires for more vendor neutral, interoperable, open standards-based modular frameworks that are going to be able to meet today's demand, but also have the ability to grow with tomorrow's capacity in mind. So essentially what we have right now is we have two separate pressures happening at the same time. On one hand, you have demand that's increasing, and at the same time, supply is being constrained. And this is, particularly true for high-speed optical components. So the question is now really, how do you scale capacity efficiently while you're being faced with both technology and supply constraints? And so this is where it becomes pivotal, and exactly why we're here today to discuss and have a common understanding of what 800 gig brings to the table. So, now that we've given these constraints in both demand and supply, I think it's important to highlight what 800 gig really delivers. But sometimes 800 gig networks are often misunderstood. And, if we take a look at the simplified graph up here, the model at 400 gig is shown as 75 gigahertz, 100 gigahertz spacing, and you have 64 channels per band that give you around 25.6 terabits of total fiber capacity. And at the 800 gig model, the spacing changes. It's 150 gigahertz spacing, but the amount of channels is reduced in half to 32. But again, you're sitting around 25.6 terabits of total fiber capacity. And so the first point here is that moving from 400 gig to 800 gig does not automatically increase your total spectral efficiency of your fiber. And that surprises a lot of people because they often assume that, doubling the per wavelength rate, must directly translate to more total capacity per fiber. But in reality, you're using a wider channel for each 800 gig wavelength. And so the aggregate capacity remains essentially the same. But so if we say that and we say, well, if 800 gig does not give you more fiber capacity, what does it give you? Well, it gives you two very important things. It gives you, first, economic benefits And secondly, it's going to give you architectural benefits. So let's peel that back a little bit, because when we look at the above scenario, if we take our eye off the total capacity, what we need to realize is with 800 gig, you need fewer wavelengths, about half when you're comparing 400 and 800 gig. You need half the amount of wavelengths to carry the same total capacity. Now, when you're talking about reducing the amount of wavelengths, fewer wavelengths means fewer optics. It means lower power consumption. Lower power consumption per transported terabit. It gives you higher density, and oftentimes it builds you a much more simpler scaling model. So 800 gig is not mainly a spectral efficiency story here. It has become a story of economics, it's become a story of density, and it's become a story of architecture. But if 800 gig does not change the physics of fiber, it really does change. What it does change is the economics of how you're filling that fiber. And before we, dive into the benefits of 800 gig, I think we should, take a moment to discuss and address what 800 gig does not solve. So 800 gig doesn't solve for any of your physical fiber limitations. It doesn't change your OSNR, it doesn't change your distance, it doesn't change your fiber characteristics. All of those remain the same. And it doesn't give us more available capacity, because 25.6 T or 51.2 T of 400 gig is the same as it is in an 800 gig world. So let's talk about some of the practical gains that we get from 800 gig. And we touched on this earlier, but with fewer wavelengths in the same overall capacity can be carried with half that number of wavelengths, your systems become operationally simpler and essentially more economically attractive in the same vein. Now, the second gain that you probably realize is the lower cost per bit. And in the right scenarios, we're seeing 800 gig optics that can compare favorably against two 400 gig optics. And I think for those of us that have been here for long enough, this trend has been proven over time with the 10 to 100 gig and 100 gig to 400 gig optics, economical narrative playing out over time. But the third gain that you're going to get is a lower power per terabit. So if you're essentially transporting more traffic with fewer optics and fewer platform units, your power efficiency improves. And this leads you to the fourth gain is you are able to operate with higher density. So we can look at things like the PacketLight 8000G model, where we position 8 terabits in a 1U chassis, which is the kind of density story that matters today. Because when we're faced with scaling demand that supports AI and data center interconnects and constrained rack environments, so this is where density truly matters. And I think at the core of it, the value proposition for 800 gig is that you get the same or similar fiber capacity in the immediate C-band framing, but you get a much more efficient way to deliver that capacity. And the reality here, something that we touched on very early in the opening sections of this, is that most networks are brownfield. They're not greenfield. We're not also blessed to work with greenfield networks. So the brownfield networks present another challenge, because in existing networks, you have installed MUX and DMUX components, you've got established filter spacing, you've got pre-existing ROADMs that may not be FlexGrid, may or may not be FlexGrid. You've got amplification plans that were designed around earlier wavelengths and spacing assumptions. And this is really the foundation where the brownfield challenge begins, because the existing networks that we have historically operated in are using 50 gigahertz, 75 gigahertz, or 100 gigahertz spacing, and often with fixed grid assumptions. But the challenge with 800 gig fundamentally here is that it requires a wider spectrum allocation. And that's represented here on the screen as the 150 gigahertz spacing. What it does is it requires more flexible handling of the existing spectrum and routing in the brownfield networks. So the problem right off the jump is not straightforward as we would like it to be. It's not just a simple answer of taking an 800 gig wavelength and plugging it into most existing legacy optical infrastructures, because you can't do that without checking whether the filter plan, the ROADM behavior, the spectrum availability can all support that. And this is where many teams that we talk to discover that adding 800 gig is not just the next incremental upgrade. It is fundamentally, it's a compatibility and architecture problem. So let's take a second and look at some of those challenges. When you overlay 800 gig onto the legacy networks, it's not just a simple configuration change. It's honestly, it often becomes an architectural conflict. And there's three main reasons for that conflict that we see. The first conflict is your filter mismatching, because you're using 50 gigahertz, 75 gigahertz, or 100 gigahertz spacing, but an 800 gig signal needs a wider 150 gigahertz slot. Then your existing filter plan is going to reject or distort that signal. And the second conflict is there are ROADM limitations. So non-flex grid ROADMs are not designed to dynamically allocate these wider custom spectral slots that 800 gig requires. So even if the wavelength exists, the switching fabric downfield may not properly support it. The third conflict we found is spectrum fragmentation. And that's because brownfield networks are not clean slates. There's often existing wavelengths that are occupying non-contiguous portions of that spectrum. So even if you have, for example, in theory, enough total spectrum, there may not be a wide enough contiguous block available for that 800 gig. So the issue in this scenario that we're discussing in the spectral allocation is not just bandwidth demand. The challenges that we're faced with now are, the bandwidth demand, but you're also talking about your spectral compatibility, your spectral availability, and your legacy infrastructure. So now we've talked about, a few of the challenges in the 800 gig migrations. We're going to move on to my favorite part, which is, talking about solutions to solve for these challenges. And, I think the first migration path that we can consider from a fundamental conceptual perspective is the L-band expansion. And the idea here is simple. Say, for example, your C-band is full or effectively spectrally constrained. You add your L-band and you use it as additional spectral real estate. So realistically, when you open up the L-band, you can add another 32 wavelengths of 800 gig, which effectively doubles your total fiber capacity from 25.6 T to 51.2 T. And that's when you have combined both, max capacity for both C and L bands. And we see that this is attractive because when you're talking about things like fiber exhaustion, the L-band option gives you an immediate way to extract more value from the existing fiber without resorting to new fiber construction or leasing more fiber. But the caveat, it's not free, and it requires the right technical ecosystem to navigate, the L-band expansion option. And there's things like L-band capable amplifications that you need. You need splitters, you need the MUX demux infrastructure, and the platform. You need the platform that supports that expansion model. And the way that we see it is the L-band is a very powerful expansion path, especially when your fiber is exhausted, but it's not usually the first or the simplest answer for every scenario. And that's primarily because not every platform supports L-band in the exact same way. So we'll take a quick look at a visual here that just gives us, so what we see on the top is a depiction of your spectrum allocation with the C-band carrying 64 channels of your 400 gig and the L-band carrying 32 channels of your 800 gig. And that together is combined for 51.2 T over the same fiber pair. And on the bottom, you'll see a full allocation of C and L bands for 64 channels of 800 gig at 51.2 T. So one thing that we do have to note here is that the 100 gig pluggable models are not always easily supported in L-band, but 400 and 800 gig pluggable models are supported in both the C and the L-band. And that's an important distinction because if you're looking at 100 gig networks to 400 gig to 800 gig, you being cognizant of where you're placing what capacity and what band. And that brings us to our second option, which we feel is probably the best path for consideration. And there's a few reasons, we'll get into that. But the second option we see is the FlexGrid ROADM. And this is where your architecture, I would describe this as the long-term direction, the long-term play. And that's because FlexGrid solves for the inefficiency of forcing every service into the same fixed spectral mold. We'll take a look at some examples here in a minute. But with FlexGrid in the simplified, model that you see on the page here, the 100 gig wavelengths can use a narrower slot. The 400 gig wavelengths can use a medium slot, and the 800 gigs can use a wider slot. And this is important to understand. That means that you can mix your services much more efficiently on the same fiber. And so instead of wasting, wide spacing on lower legacy rate signals, you're essentially matching the spectral assignment to the service. And this is a huge improvement for brownfield migrations. And that's primarily because it lets you carry along with your legacy and your new services together in a much more optimized way. And, I think to note here is, from a long-term perspective, why we recommend this option is this positions the network for your future capacity growth into 1.6 T and beyond. And so the real strategic point is that FlexGrid is not just about supporting 800 gig. It will do that for day one, right? But it's also, and I think we've touched on this throughout the webinar, it's about avoiding another redesign when 1.6 T and future rates become relevant. So that's why we highlight FlexGrid as the preferred option, because it's both a future readiness architecture and an 800 gig feature enablement for today. So from a visual perspective, you guys can see the example here. On the top left, you have 400, 200, and 100 gig wavelengths with either 175 or 50 gigahertz spacing combined. And below that, you look at 800 gig that requires 150 gigahertz spacing. And on the bottom, in a fixed grid model with 150 gigahertz spacing, you can see how that would have to accommodate that spacing for all of your legacy lower rate signals. And then on the right-hand side, you'll see the visual depiction of how much more efficient a FlexGrid system can be, because you're combining a variety of wavelength capacities, but also accommodating their appropriately varied spacing requirements. Now, we would be amiss if we said that, this is not every network is ready for a full FlexGrid transition if they're not there today. And that's where a third option becomes useful for consideration. So the third migration path that we're going to cover today is what we call the hybrid spectrum split. And this is often the most pragmatic answer for a lot of customers because they need to protect their existing services and at the same time begin that controlled move toward 800 gig. And the concept here is essentially to partition your available optical spectrum into, two practical domains. One portion of that spectrum remains allocated to your legacy 100 and 400 gig traffic, and that preserves the existing infrastructure and greatly minimizes disruption. And then the second portion is assigned to the 800 gig wavelengths using the appropriate spectral allocation. And this is a valuable approach because it creates a phased migration model, and you don't need to build everything at once. So this is important because you can preserve service continuity, you can reduce risk, and you can introduce 800 gig where it delivers the greatest, and I say this, immediate value while you work towards other aspects. So this is particularly useful approach in brownfield networks where there's a large level of the scrutiny on service disruption. There's heightened awareness around operational caution, or there's even incremental budget cycles that make a full redesign difficult. So those are the three logical methods of migration that we see. And the real question I think that we want to cover here is, well, when should each migration path be used? And candidly, there's no universal answer here. The right choice totally depends on the state of the network and every individual network's growth path. So if the C-band is effectively exhausted and the operator needs max expansion from the existing plant, well, L-band becomes very relevant. If you're making a strategic upgrade and you want the architecture that supports the best mixed rates and need the future evolution, well, then FlexGrid ROADM is the best answer. If the network demands a controlled, low disruption migration path and protects the existing services, well, then the hybrid spectrum split is often the most practical choice. So what this does, this slide here really represents a decision framework. And the question is not, do I want 800 gig? That's the wrong question. What we need to be asking is really, what problem am I solving for? And what is my architectural starting point? And I think if you ask those questions, you'll end up at a very good foundational point of where to start. But there's another design debate that's happening in parallel that we also want to discuss, and that's the IP over DWDM versus optical layer discussion. And there's a ton of market momentum behind IP over DWDM, and the promise sounds attractive, right? You plug coherent pluggables directly into your routers, you simplify the architecture, and you reduce your layers. And for some hyperscale type environments, this can make perfect sense. But what we began to realize when we're talking to a lot of enterprises, carriers, and transport-oriented environments is that the IP over DWDM model hides an important problem. That's not to say that there isn't a place for it in the network, but the problems here is that the IP lifecycle and the optical lifecycle are just simply not the same. And that's because routers don't get refreshed on the same cadence as your optical transport and the economics behind optical transports. So if you've just invested heavily in a router generation, you may not be ready to refresh that entire layer just because the optics economics have shifted in favor of 800. So if your optical scaling becomes directly tied to your router refresh timing, you lose two very important things. You lose flexibility and you lose economic freedom. And that is what we see as the hidden cost to IP over DWDM, and remains the key elements to why the dedicated optical layer is still necessary. And the dedicated optical layer is going to allow operators to realize three very distinct important advantages. The first we just covered is the lifecycle decoupling, because it allows you to evolve your IP layer and your optical layer completely independent. And according to their own, your IP layer economics and roadmaps and your optical economics and roadmaps. It allows you lower cost scaling because you can add wavelengths and optical capacity without requiring an entire full router platform change. And the third being flexibility, meaning that you can mix your rates, you can support multiple service types, and you can interoperate across environments without tying yourself to a single router-centric scaling model. So the key value of the dedicated optical layer is not just technical purity, but it's operational and economic freedom. So let's take a look at that in a little bit more simple economic perspective. Because when you transport a given amount of traffic using two 400 gig optics, you typically consume more optics, you consume more power, more rack space, and more management overhead than if you transported that equivalent traffic using just a single 800 gig optic in the right use case. So, we forecast in about 2027, the price of your 400 and 800 gig modules will be the same. And so at that point, it'll cost you twice as much for the same capacity on a 400 gig network. And this is essentially the foundation and the basic economic logic behind what is driving 800 gig adoption today. So again, the point is not that your fiber suddenly carries more total capacity. The point is that the network carries that capacity more efficiently, more economically. So when you're evaluating 800 gig, the right question is not only how many terabits do I get, but the right question is how many terabits do I get per rack unit, per watt, per optic, and per operational step. And this becomes even more tangible when you look past just a one-time deployment and you take into consideration both density and scale. And density is one of the most strongest practical arguments for 800 gig. In this case, we compare 4.8 terabit classes with 8 terabit classes, which provides significant increase in the capacity per unit of space. And that matters in real deployments because AI and data center interconnect and dense data center environments, the network is not only constrained by fiber, it's constrained by your rack space, your power budget, and your cooling. So if you can get more transport capacity from the same footprint, that directly improves the business case and your deployment flexibility. Sean, should we fast forward?
Yeah, if you don't mind. We're kind of like running up against the hour, but I think there's a lot of great information here, and folks, if again, let me just emphasize to the audience. Everybody can. PacketLight is happy to follow up with anybody that has any questions that we may not get to because as we often do because they're the sponsor, there will be an opportunity for folks to follow up. So yeah.
Yeah. So let me leave you with this, right? I think the operational reality is that these decisions are being driven by compact one rack unit systems with the ability to mix 100 gig and 800 gig, provide encryption and no port licensing models that support clients' modular growth. It solves for today's, but also enabling for tomorrow. So the largest point here is that deployment speed and architectural simplicity matter. And that's in a market with both migration complexity and supply pressure. So a platform that's compact, it's modular, it's easy to scale, has a real advantage. And you can see that in some of the PacketLight offerings with our 8 terabit transponder, the PL8000G, where you can provide up to 8 terabits of transport in a compact 1 rack unit device, and supports a mix of client handoffs for 100 gig, 400, or 800 gig, allowing for the client to have flexibility in their deployments. And then the PacketLight 8000M, which enables the entire optical layer as either a muxponder or transponder, but also providing amplification and optical switching in these units as well. So this is what we see as the way forward for providers to help them navigate that migration to 800 gig, given the impacts on the brownfield network that we've discussed today. And at the final end here, if you want to download the slides, you can see a little bit about a phased approach that we wanted to close with. So phase 1 is work your way toward a stable 400 gig foundation. Right? Phase 2, introduce FlexGrid capability, because that's the architecture that's going to take you from fixed speed to a more adaptive spectrum model and enable future iterations of capacity growth.
AI tools that let you create, edit, repurpose
network, and then in phase 4, you have the L-band to expand. So thank you very much for your time, everyone.
Great. Well, thanks, Erik, and yeah, I appreciate it. Lots of really great information here that I look forward to following up with PacketLight on. Always really great. You guys always have like a lot of really great information in every webinar. Let me thank you, Erik, of course, for being a speaker and sponsor, as well as my old friend Lawrence Gassman for also coming on and kind of setting the stage. Just earlier, I mentioned I just want to address the Bixby process again. Earlier, I mentioned the webinar qualifies for a CEC from Bixby. Here's how that works. Basically, as I understand it, so we'll basically just you'll get a link, I guess, to an attendance certificate. This personalized view will have your name as well as the title of the presentation, today's date, and a code that Bixby will recognize for one CEC. As a reminder, you need to stay, well, everybody that's on the webinar to get to that. So just look for that link, and you can click on that and get what you need. And just once again to remind everybody, the webinar will be available on demand for viewing for 6 months after the broadcast day. If you view the webinar on demand, you'll need to complete a short quiz at the end. Once you complete the quiz, you'll receive an email with a link to your Bixby certificate of participation. But again, I encourage everybody to, look at it on demand and share with other folks. I think there's a lot of great information here that Erik and Lawrence shared today. So thanks for that. And thanks everybody, for attending. I really do appreciate it. And again, thanks to PacketLight again for being a sponsor, and Lawrence for showing up to help us out. Thanks again. Great. Thanks very much.
Thank you, Sean.
Great.